Well, hello everyone. This is SanfordFlipMath. For those of you in pre-calc, welcome back. We've been doing this quite a bit this year. And for those of you in calculus, welcome to FlipMath. This is your first lesson. Just so you know what's going on, we are videotaping the quote lecture part of what's going to be taught, and then in class we will discuss it at length. So this is calculus now, chapter 2. We are talking about limits. So for the calc class, this is a review of what we did at the end of pre-calculus, and for those of you in pre-calculus, we've been working all along, but we just switched to the calc book just for this one chapter. Just a quick reminder that if there's anything that you miss, obviously you are in control of watching this video. You can pause, rewind, you can just write stuff down, not write stuff down. It's entirely up to you what you feel you need to do. You are the boss, okay? So let's get started. Okay, so first thing I need to point out, this is actually from your calculus book from page 60, and this is the definition of what a limit is. This is a lowercase Greek delta. This is a lowercase Greek epsilon. And I'm just showing you this so you see it. Typically, this definition is not used very much. It is the standard definition, but I just want you to have an awareness of it. So what the notation is going to look like is that. And just a reminder that what this means is, this is kind of like what the end behavior notation was, and we actually see this when we're doing end behavior. I pointed out to you and then just say, we'll talk about this again later. This says as x approaches c, as x approaches whatever that number is. Okay, so we're representing it with a c right now. Okay, y approaches, and by approaches I just mean it gets closer and closer and closer to some number, whatever that number is, and we're just saying L. Okay, so we're just saying that as x approaches some value, this is what y is getting closer to. As x gets closer and closer to some value, this is what y gets close to. A quick example. Let's say we're going to do the limit as x approaches 2 of 3x. Well, there are lots of ways we can do this. One way is we could actually graph what y equals 3x looks like. Okay, so here's 1, 2, and let's adjust this just a smidge. So 2, 4, 6. Well, if you notice, as we get closer and closer to the x value 2, it looks like y value is approaching 6 from that side. As we approach 2 from this side, it looks like y is approaching 6. So I'm going with 6. Now that was kind of a graphical explanation. Another way to do it would be to look at like a little table of values. Sorry about that. So maybe I have 1, 2, 3, and I'm talking about 3, 6, 9. As I approach the x value 2 from that way, the y value is approaching 6. From that way, the y value is approaching 6. So again, that's a numeric approach. Okay, another thing that's cool about this particular problem, this problem is actually way easier than that, because if I look at y equals 3x, it's a continuous graph. There's nothing goofy going on at 2. I can actually just stick that 2 in there. So you guessed it, and some of you I know were ahead of me, but 3 times 2 is 6. All right, so what we just looked at is one of, actually a couple of the ways that you can approach limit problems. One of those methods is substitution. So again, if the value, so we're talking about the limit as x approaches some number of f of x equals some number. So this is the x value it's approaching. This is the y it's approaching. Okay? So if f of x, if whatever this function is continuous at c, you can just substitute c in and actually get a value. So that's kind of cool. So there are tons and tons and tons of equations that, types of functions or whatever that would work for. So like for instance, I could do the limit as x approaches 2 of, let's say, 3x squared minus 2x plus 7. Okay, so 2 squared is 4, times 3 is 12. 2 times 2 is 4. And 7 is still 7. Isn't that amazing? So I'm thinking that's 15. Okay, so the limit as x approaches 2 is 15. The limit as x approaches 2 of that is 15. Okay, so it really is that easy when it's continuous. So if I was doing the limit as x approaches 2 of, let's say, x squared minus 4 over x minus 2, well, that's a whole different thing. Okay, so if I substitute 2 in here now, well, 2 squared is 4 minus 4. 2 minus 2 is 0. This ends up 0 over 0. Well, I can't say undefined. Technically, this would be indeterminate, and because 0 divided by 0 is indeterminate. If it was 7 over 0, it would be undefined. But all this means is I can't use substitution. Okay, there could still be an answer that that this particular function's approaching. And if you do a little graph in your calculator, you're going to find that this graph looks like this. And there's actually a point missing here. There's a hole. Okay, so with that in mind, sometimes you have to do a little bit of algebra first, so I'm kind of jumping ahead of myself, but this is just the flow of how it came out. So we're still doing the limit as x approaches 2. I'm going to do a little factoring here. Sorry to use the F word. And note that that divides out. So this limit now is the same limit as if I took 2 and put it in there. 2 plus 2 is 4. So what that means is as x is approaching 2, y is approaching 4. Okay, now just a quick little note here. I'm going to turn that equation off because I want to save it for later. So x squared minus 4, x minus 2, I believe, is the equation. Okay, and I'm going to zoom 4, and I don't know if this will show up on there like I want it to. It does not. So let me just go in, and I'm going to just change the y max. And the idea here is that I want those x values, and I did zoom 4 because I want it to count by tenths, because then it does numbers a little nicer for me. Okay, the only thing I'm really changing, so this was zoom 4, and then I changed the highest y value because I want it to go taller. Okay, all right, so let me get rid of that so it doesn't cause a problem. I don't know if it would or not anyway, but here we are. Okay, and let me switch that to a large screen graph. All right, so the interesting part about this, remember what we said was as x approaches 2. Well, this is 2. Okay, here's the y value 4, and notice that point's missing, and we've seen this back in chapter 1 in the pre-calc book. That point is a point discontinuity. It's missing. Okay, now this problem is not saying this problem does not say f of 2. F of 2 is indeterminate, but that's not what it asks. It says what's the limit as x approaches 2 of that function. Well, if you notice, as x approaches 2 from the left side, looks like it's getting close to this point, whatever this point is. From the right side, it's getting close to whatever that point is. Okay, so the question is, you guessed it, what's the point? All right, well, let's trace. Okay, and I got too much foo-foo on here, so all right, let's trace. Now notice what's going on with the x values. They're counting up by tenths. My y values are counting up also. Uh-oh, the y value disappeared. All right, let's go back. 3.9 for the y value. 4.1 for the y value. Well, I'm sure you're thinking to yourself, what number would be nicely between 3.9 and 4.1? Well, I'm going to go with 4. Now, you could see this also in the table, but the problem is it doesn't get as nice and tight. Okay, 4 is clearly between 3 and 5, but if you're looking at this numerical representation, you have less information here. Because right now, you know, how do you know it's not really going to 3.9 or 4.7 or something like that? You just know it's probably between 3 and 5, okay? So let me do one other thing here. As I said, you can put in, you can do some algebra and simplify, and when you do that, you end up with a little bit different situation. So if you recall, after we simplified, it was x plus 2. And so if I look at the table now, well, notice, so this was the simplified version. I get 4, even though this thing was error. So just, again, domain and range questions happen before simplification happens. Okay, so this y value really isn't even in the range, but it is what the graph approaches. Okay, so what we just did was a little algebraic manipulation of this equation so that we could see what y was actually approaching if we could somehow eliminate that point discontinuity. That doesn't always happen. You can't always do that. Okay, so let me just talk a little bit. We just looked at the table and the graph, and what you're looking for is where is y approaching? What is y getting close to at whatever, as you get closer and closer to that x value? That's what limits are about. Now, sometimes this can be a little frustrating or a little disconcerting, and really the reason is because we are used to, look, what's the answer? We are used to, when x is 7, I put it into the formula and it tells me 14. And unfortunately, limits are a little more soft. They're a little more vague than that. So it's a little harder to nail it down. So sometimes, if there's no discontinuity, you can substitute. Okay, we love that. But that kind of misses the point. I mean, limits are really more generally about things that you can't just substitute. It's part of it, but it's not always it. Okay, so sometimes we have to go to tables and graphs to kind of look at patterns. We're looking for, where is y going? Looks like it's going to that. Well, does it ever get there? That's a whole different question. It doesn't ask if it gets there. It says, what is it approaching? Okay, so that limit notation is about what is y approaching. Okay, what is the number that y is getting closer and closer to? Okay, so buckle up. All right, well, here's a whole bunch of jib. Thank you, Ashley Archer. Jib is my favorite word now. All right, so this is also from your calc book. It's from page 62. This is the Finney, Demana, Waits, Kennedy calculus book. And really, you have to ask yourself, what's the point? What's going on? So they're saying they have some polynomial equation function. Okay, so an example might be f of x equals 3x squared minus 2x plus 1. Okay, and they're saying if c is any real number, notice what they're doing. They're saying the limit as x approaches that number for f of x, you can find that by just doing f of that number. So I need a one-word way to say this. So this is specifically about polynomials. So this is just a theorem that's specifically about polynomials. Well, it's really the same idea that we just said back here. Okay? So every polynomial in the universe is continuous. So if that's true, if we're looking for a limit and it's continuous, we can just substitute. So this is a specific manifestation of that. Okay? You can just plug that bad boy in. Okay? Similarly, for an irrational function, notice what they did. They're saying here's c. Sorry, I covered it up. There's c. And if you want to know that limit for a rational function, okay, rational function is from a ratio null function, you can just substitute that c in there. Now there's a little disclaimer. Okay, just need to remember that not all rational functions are continuous. In fact, most of them are not, or at least many of them are not. So you can plug it in, provided the denominator doesn't equal 0. So this gets back to that discontinuity issue or continuous issue. If the function's continuous, you can just plug it in. If it's continuous, it doesn't have to be continuous everywhere. It just has to be continuous at the point you want to look at, okay? So that's just one of the theorems. I know I used the T word. Sorry, I know it's not geometry, but theorems are just they're mathematical rules. They don't have to be geometry rules. Okay, so let me just kind of point out that this is a lot of stuff. There are a lot of properties here. This is from page 61 in your book, and then it continues over to 62. Look at me cleverly taking a picture of 2 books at the same time. Okay. All right, so what's the moral of the story? We're going to try and summarize this easily, okay, because this is a lot of stuff. Now watch this. They're saying if you have one little function and you do the limit and you get some answer, you have a separate little function, okay, of that little guy, and same value you're looking at, then you can actually take those 2 answers, depending on what's going on, and just put them together. So for instance, and now, this is not hard, this is very intuitive. If you're doing the limit of this whole thing, and you know this limit and this limit separately, you can just add them bad boys up. Okay? So if you're doing the limit of a sum, it's the sum of the limits. Doesn't that sound all funny? Okay? So the limit of the sum is the sum of the limits. Okay? So, oh, isn't that nice? Look at that. Man, that was well said. Thank you, authors of this book. Okay? And this is the same idea pretty much all the way along. Okay? You see subtraction here. You can actually do those limits separately and subtract them. Okay? So for instance, let's say I have the limit as x approaches 2 of 3x plus x minus 2 over x squared minus 4. Okay? So I'm doing that limit. Well, this thing, I can just substitute in. I know that's 6. 3 times 2 is 6. So I can do that limit separately. So technically, just what I just did is I did that limit. Well, I can do this other limit separately also. So I could do x minus 2 over, this would be x plus 2, x minus 2. Now, why am I doing that? Because I know, I'm thinking that there's a way to simplify this, so now I can substitute. So this will then become 1 over x plus 2, and just a reminder, I can't just substitute this 2 into the original, because 2 squared minus 4 is 0. I can't divide by 0. That's a problem. But now, sorry, yes, no, that's it. But now, I can substitute 2 in and say, this is 1 over x plus 2. 1 over 2 plus 2 is 1/4. So that whole answer for that limit is 6 1/4. Okay? So the idea is you can break it up piece by piece, and it's very intuitive. If you're looking at subtraction here, you can subtract limits. If you're looking at multiplication here, you can multiply limits. If you have a number, a constant multiplying, you can do the limit first and then multiply by the constant. Okay? If you have division, then yes, you can do the limit of the numerator and denominator separately, and then just divide them. Now again, denominator can't be 0. Okay, that's always the case. That's not even a number. Okay, and even if you're raising something to a power, you can do the limit first and then raise that answer to the power. Okay, so that's legal also. Okay. So that's the speedy version of all of this. So then in class you're going to be doing a bunch of examples of this from the book. Okay, so again, let me just do a speedy recap, even though I know you can rewind. Okay, so those were the properties. Sandwich theorem, we will deal with that later. I think that's in the next lesson. Okay, okay, so you can do limits by substituting, by looking at graphs, and also sometimes you are going to do some simplifying, either with properties or factoring, some kind of algebra kind of thing, and then you can go back to either substitution, table, or graphing. Okay? Again, you can rewind, pause, do whatever you need to do to learn what's going on, and we will see you in class. Thank you much.